Solve for a number of integer a which makes the quadratic function y is equal to x squared minus 2ax plus a squared plus a plus 3 remains in the second quadrant. Before we solve for this question, let's think about the types of the vertex in the quadratic function, which will going to be the possibilities. At first, there are two cases, and they're all defined by the leading coefficient of the quadratic function, which we usually notated as a value. The reason why we notate it into a value instead of notating specifically is because a value always change depends on the situations. And a value, which will going to be the leading coefficient, is greater than 0, which means when the a value is positive value, remember that the leading coefficient is a coefficient of the highest power. And when the a value is greater than 0, the graph of this function, or the graph of the quadratic functions, will go upward. When the quadratic function goes upward, it will look something like this, that keeps going toward upward. And if the quadratic function goes upward, it will contain only one point, which will going to be its minimum value, which we also call it into a lowest point of the quadratic function. And this will going to define when the leading coefficient, which we usually notated as a, is greater than 0. And for the second case, it is also defined by the a value. And when the a value, which will going to be a leading coefficient, when it is less than 0, which means when its value is negative value, the graph of this quadratic function will go downward, unlike the first one. When the quadratic function's graph goes downward, for example, it will look something like this, that keeps going downward, or we usually call it opens downward. It will contain a point which will going to be its maximum point in its quadratic function, which we usually call it as highest point of the quadratic function. And it is also defined when the a value, which we usually call it as the leading coefficient, is less than 0. And if you think about the term of a vertex, vertex is a term where it is an addition of the number of possibilities of minimum point and the maximum point. So the addition of these two number of possibilities will going to give us the vertex. We can clearly see that the leading coefficient in this quadratic function y is equal to x squared minus 2ax plus a squared plus a plus 3. Leading coefficient, which will going to be the highest powered x terms, it will going to be 1. So the 1, so if you write our function down, y is equal to 1x squared, we can just write it as x squared minus 2ax plus a squared plus a plus 3. So our leading coefficient will going to be 1, but we can see that 1 will obviously going to be greater than 0, which means a value, our leading coefficient, is greater than 0. So according to our property, the graph of this quadratic function will go upward, and that results in our conclusion that this quadratic function will going to contain our minimum point. But in our questions, they try to tell us solve for the integer a right over here. That makes this quadratic function vertex, it should be vertex, remains in the second quadrant. So the most important thing in this question was going to be the vertex of the quadratic function. But if you look at our function, x squared minus 2ax plus a squared plus a plus 3, usually when you try to find the vertex in a particular form, which in this case, this form is a standard form. We usually convert the forms into a vertex form in order to find the vertex easily, which is also equal to completing square. So we had to complete the square or make it into a perfect square form in order to solve for the vertex of the quadratic function. But if you look at our function right now, so we have to complete the square. But if you look at our function now, it contains too many unknown variables, three a's. So we need to find another way in order to solve for the vertex of the quadratic function. There is a way where we don't have to convert our, in order to solve for the vertex form into a complete square form, which we usually call it as perfect square form. But we won't be able to solve for it or prove this situation or this formula in this video, and we're going to be prove it in the next video. So the way to find the vertex of a function instead of solving it or converting it into a perfect square form is to use our formula, and our formula is usually the vertex of the function. When you convert it into a coordinate, it is made of x comma y, and our formula is just trying to solve for the x value of our vertex. The reason why we don't really have to solve for the y value is because we can figure out that x value is our input of our function, and our y value is our output of our function. Which means if you just know the value of our input, which will going to be our x value, we can just input our values into our function. That means according to that function or according to the equation that it contains, you're going to form a output of our function, which we're going to find the y value. So let's think about the ways to solve for this x value of our vertex. So again, I won't be able to prove our situation, our new formula for the vertex, and I'm gonna prove it in the next video. And again, with the formula, another real coordinate that we're gonna create will going to be negative b over 2a, comma y value. And the difference between the normal coordinate and this coordinate will going to be this coordinate is optimized when it comes to solving for the vertex. Negative b over 2a is our x value. Y is just our y, which will going to be the output. The reason why this is useful is because if we just apply our formula, we don't have to convert this into a vertex form. So if you write this down more neatly and then more like in the last font, we're going to be negative b over 2a and then comma y. And let's think about each functions of each variables, because there are two variables which will going to be b and then a. And let's think about the a first. But we need to know that this is all vertex coordinate. A and a b exist, so the first thing that we're trying to find is the a value. The a value is the same kind of notation that we use to solve for the types of the graph. The a value is a leading coefficient of our quadratic function. Let's think about the function of the b. The b will going to be the first power terms coefficient, or first power variables coefficient. So essentially they're all coefficients, but the locations are different. So only thing that we need to memorize is the a and then b, which actually defines our x terms of the vertex that is more efficient than converting our standard form or the binomial form into a completing square form, which we usually call it as a perfect square form, to find the vertex of the quadratic function. So let's actually apply our negative b over 2a. So if we actually apply our formula to our original question, and our formula was negative b over 2a, and we are essentially trying to solve for the x value or vertex of the function. So the b will going to be the coefficient of the first power variable, and our first power variable is negative 2ax. But we're trying to find the coefficient, which means it is essentially a constant that is attached with the variable, which will going to be x. So our coefficient will going to be negative 2a. So we can write negative, and we still have negative. We can write negative 2a. And for the denominator, we have 2 times a. So 2 times a will going to be the leading coefficient, which will going to be 1. So if we finish our expression, it will going to be negative 2a. So there's negative, and we have negative 2a over 2. So if we finish our calculation, 2, negative 2, and then 2 cancels out as negative a, but we still have the negative in front, right over here. So this will going to be end up being just positive a. So we can see that our x coordinate of vertex will just going to be a. So if you write our vertex down, we can write it as a comma y. And for solving for the y, we know that a is our input of our function, which means if we input our x value into every single x terms, which we usually call it as vertex, variables, we'll be able to solve for the output of our function, which will going to be y. So we need to write our quadratic function down again. So our quadratic function is y is equal to x squared minus 2ax plus a squared plus a plus 3. If we input a into our x value, we're going to get y, which we're going to find is equal to, instead of x, we input a, we still have square, minus 2a. We input x value as a times a will turn to a squared. We still have a squared because there is no variables right over here. So we can write plus a plus 3. So in order to find the value of the y, which will going to be our output of our function, all you have to do is we need to simplify our expression. A squared, so a squared plus a squared becomes 2a squared. We have minus 2a squared. And we have our leftover, which will going to be plus a plus 3. So 2a squared minus 2a squared simply summed up as 0, and we still have plus a plus 3. So we can see that as our answer, y value or y coordinate of a vertex of this quadratic function will going to be a plus 3. So if you finish our notating the vertex of a quadratic function, we got a comma a plus 3. So the most important thing when it comes to solving for a vertex in the standard form, which was our original function right over here, instead of converting into a vertex form, which is also essentially converting or completing the square, all you have to do is we can apply our formula for it. But the proof of the formula is also important, and I will be doing it in another video. So for x value, the x value of the quadratic function was negative b over 2a, which we found it as a. We don't have to memorize the formula for the y, because y is our output of our function, which means if we input our x value, which was a, we're going to get an output of our function, which we got as an a plus 3. And our a value was x. Convert our statement into a realistic our coordinate plane. This will going to be our x-axis. This will going to be our y-axis. And for the second quadrant, this will going to be the first quadrant. This will going to be the second quadrant. This will going to be the third quadrant. And this will going to be the fourth quadrant. But the most important thing here is that the x-axis, the point on the x-axis, and the point on the y-axis doesn't count as a quadrant. So the vertex of the quadratic function stays at the second quadrant, which will going to be somewhere, I'll just approximate value. And our quadratic function opens upward, which will going to be like something like this, that keeps going upward. And our vertex right over here will going to be a comma a plus 3. This will going to be our vertex of the function. But if you want to solve for the a value, which makes the quadratic function stays in the second quadrant, we need to solve for it. So if you write our vertex down again, vertex was a comma a plus 3. And if you think about the properties of the second quadrant is where the x value should always be equal to negative. And we can also see it right over here, where the x value is always negative. And for our y value should always be a positive value, which we can see through right over here. And if the values satisfy these two statements, then the quadratic function or some points can rely on our second quadrant. So we can kind of think about it in this way. The x value should be equal to negative, and our given coordinates of x value and the y value will going to be a comma a plus 3. And from here we can apply our theory that our x value in this vertex is a, and our y value of our vertex is a plus 3. So we can say that x value should always be negative, which means in this case the x value is equal to a. So the a value should always be less than 0, which shows our first statement true. And this was our first equation, where we call a is greater than 0 or a is less than 0 into the inequality. An inequality literally stands for the equation that is not equal, which means one side can be either greater or less, or smaller. So we can write it as inequality. And then we need to always remember that inequality, whenever it occurs, it shows the range of something or some particular unknown quantity. And for the second inequality that we can find is that our y value should always be equal to positive, which means our a value, which is a plus 3, should be positive, which means our a plus 3, which will going to be our output of our function, in our way, our y value should be greater than 0. So there is our two unknown quantity inequality, and then we're trying to find the values of the a. But we need to be careful that when you're trying to find the value of the a here, we need to solve for the a value that satisfies a is less than 0 and a plus 3 is greater than 0, which means we need to use our simultaneous equations to solve the range of unknown variables. And this was the most important things when it comes to solving for these particular questions. First, if we write our inequality down again, a is less than 0. And the second one was a plus 3 is greater than 0. So for the second one, we can simplify this more further, which means a. So we can simplify this in this way. A plus 3 is greater than 0. We can subtract 3 to the both sides in order to isolate our a term. And we're going to get our a is greater than negative 3. So we can simply write our inequality down again. First one was a should be greater than 0. Second one should be less than 0. Second one was a should be greater than negative 3. And if we solve for the a value to satisfy these two inequality, which will going to show us the range of the range of the a will going to be the value that keeps this quadratic function stay or remain in the second quadrant. So if we make this into a one statement, we're going to look something like this. A should be less than 0, but greater than negative 3. So we found the range of the a, but we are not done yet. Our ultimate goal of this question, was solving for the number of the integers, not just a inequality. So if you think about inequality, these terms means the a value doesn't include these things. So the a value doesn't include negative 3 and then 0. They're beside negative 3 and then 0, which will going to be negative 2 and then negative 1. And these are solutions for the a value, which makes our quadratic function stays in our second quadrant. And if you think about how many there is, the a value, we can see that there are 2 a's. So we can see that our answer for this question will going to be 2. Or we can see that there are 2 a's, which makes this quadratic function remain in the second quadrant.